Hello, and welcome to Shimadzu's Theory and Key Principles series on gas chromatography. This is session 5, where we'll be looking at alternatives to liquid injection. My name's Ollie Stacey, and I'll be your presenter for this session. I'm part of the GCMS technical team for Shimadzu in the UK. This is the 5th session in our Theory and Key Principles series. If you missed any of the previous sessions, I recommend you watch them and then sign up to the next available slot for this session. All previous sessions are available on demand and can be accessed via our website. Please continue to join us over the coming weeks, where we'll be further developing our knowledge and understanding of GC. In this session, we'll look at Headspace, solid phase microextraction, thermal desorption, pyrolysis, and gas sampling valves. This session is designed to give an overview of a selection of the most common sampling techniques outside of liquid injection. We will cover the fundamental concepts of the techniques and applications they're commonly used for. The main purpose is to expand your understanding of the versatility of gas chromatography, rather than going into full details of each sampling technique. If you would like to know more about the specifics of each technique, or how it might help you, please contact your local Shimadzu office. We'll provide details on how you can find your local office at the end of this session. So let's start by looking at headspace sampling, which is the most common sampling technique in gas chromatography after liquid injection. Headspace is simply the name given to the gas phase above the sample. It's a sample pre-treatment technique which enables the separation of volatile organic compounds, abbreviated to VOCs, from a difficult sample matrix, which can either be liquid or solid. In chemical analysis, the sample matrix refers to anything in the sample that isn't of analytical interest. A sample's matrix will obviously depend on the sample itself, but it's also subjective and will depend on the analytical outcomes. Two different analysts might see the same sample as having very different matrices. One of the most common applications for Headspace GC is blood alcohol content analysis, where the alcohol content is of analytical interest and the remainder of the blood, the proteins, water, metals and salts, is the matrix. Another common test for Headspace is residual solvents in pharmaceutical products, things like tablets and creams. In tablet analysis, the content of analytical interest is any solvents that have been carried through from manufacturing. The matrix would then be active pharmaceutical ingredients, or APIs, and any excipients, such as bindings, coatings, and colorants. Finally, Headspace is commonly used for the analysis of toxic VOCs in wastewater. These VOCs are tested within a matrix, predominantly of water, but also of some other content that I'll leave to your imagination. In a sealed vessel, molecules can either exist in the sample phase, which corresponds to the liquid phase in this example, or in the headspace phase, which is the gas. The percentage of a compound's molecules in the headspace relative to the sample is known as the partition coefficient, or K. The larger this number, the higher the percentage of an analyte in the sample compared to the headspace. Each compound has its own value, which varies depending on the conditions. K is calculated by dividing the concentration in the sample phase by the concentration in the gas phase. Here are a few K values for common solvents in an air-water system at 40 degrees. At the top, ethanol has a huge value, meaning it remains predominantly in the sample phase, whilst cyclohexane's tiny value means that this analyte partitions heavily in the headspace. These values make sense, given the like dissolves like principle. The more polar solvents have a higher affinity for the very polar water, whilst the non-polar solvents jump at the chance to avoid it. Another factor impacting the concentration of analytes in the headspace is the phase ratio, or beta. In a standard 20 ml headspace vial, this is simply defined by the volume of the sample you add. The more sample in the vial, the greater the concentration in the headspace will be, because the headspace volume has been reduced. This means that both a smaller partition coefficient and a smaller phase ratio will result in a higher headspace concentration, thus providing higher sensitivity. When we combine both partition coefficient and phase ratio, we can see that the original sample concentration is directly proportional to the headspace concentration, but only if we keep K and beta constant. This is absolutely critical for quantitative headspace analysis. The volume of sample in the vial and the temperature the system is equilibrated at will heavily impact the headspace concentration. If we want good reproducibility and accurate results, these factors need to be kept constant. We saw in the last slide that polar analytes in water have a very high K value, which results in lower sensitivity. One way to improve sensitivity, or reduce K, is to heat the sample. This is commonly referred to as incubation. As we can see in the table, increasing the temperature from 40 to 80 degrees has a huge impact on K. Heating our sample has two key benefits. Firstly, it ensures a constant temperature and therefore gives a stable K value that's absolutely critical to highly precise and accurate measurements. Secondly, as we've said, it reduces K to boost concentration in the headspace. We can also boost sensitivity by adding inorganic salts to liquid samples. This is a technique known as salting out, and this helps to further reduce K. As we know from the last slide, K is impacted by sample matrix, so we have to be certain this is maintained. To do so, an excess of salt is added to fully saturate the sample. It's also vital that the same salt is used, as this will affect the matrix. So, if you use ammonium chloride for half your samples, it's not okay to switch to sodium chloride for the remainder. Also consider that adding salt will reduce the headspace volume, altering the phase ratio. So it's essential the same mass of salt is added to each sample to ensure consistency. As well as heating, samples tend to be shaken or agitated. It's important to highlight that this does not help improve the sensitivity. What it does do is speed up the amount of time we need to heat the sample for in order for it to reach equilibrium. It's extremely important that samples are only analysed at equilibrium. If sampling is performed before this, the sample concentration is in a state of flux, which can significantly reduce precision and accuracy. Headspace can be performed manually or using an autosampler. It's not possible to use a liquid autosampler to perform headspace analysis, but there are multi-purpose autosamplers that can perform liquid, headspace, and a variety of other sampling techniques. For headspace, there are two main types of autosampler. The first is a dedicated headspace sampler. These systems offer the best sensitivity and reproducibility, and use what's known as a loop system. The second type of autosampler for headspace is the multi-purpose solution we mentioned earlier. These use a gas-tight syringe to draw a sample from the headspace. These systems offer maximum flexibility, even enabling analysts to perform liquid and headspace sampling automatically without any user intervention. The next technique to look at is solid phase microextraction, which you'll often hear referred to as SPME or SPME. SPME is another technique that can be performed manually or using a multi-purpose sampling system. SPME is a sample concentration technique that can be used with both liquid and solid samples. It's commonly used when headspace sensitivity is insufficient, or when looking to analyse semi-volatile organic compounds, or SVOCs. SPME uses a solid sorbent or liquid polymer to trap analytes on a probe. The trapping material is coated on a fibre which is supported on a SPME probe. The probe itself consists of a body, an injection needle, which pierces through the vial and inlet septa, and a fibre, coated in the absorptive surface. It's not a hugely common technique, but has applications in food and beverage aroma and flavour profiling, where extremely low concentrations of compounds can significantly impact taste and smell. It's also used in some labs for very low-level environmental pollutant analysis. One of the nice things about SPME is that liquid samples can be analysed in a similar way to Headspace, known as Headspace SPME. But they can also be analysed by direct immersion, where the fibre is submerged in the liquid sample itself. Headspace SPME follows the same principles of standard Headspace, and is best suited for analytes that are very volatile, as it's easy to extract them in the Headspace phase. It's also best when the sample is solid, or has an extremely dirty matrix. As with traditional Headspace, matrix modifications, such as the addition of salt, can be used to reduce the K value and improve sensitivity. Headspace SPME, however, isn't well suited to lower volatility or more polar analytes. In this situation, immersive SPME is more well suited. Overall, direct immersion or DI SPME tends to give higher efficiency extractions, resulting in higher sensitivity. But this can be negated if the sample has a very dirty matrix. DI SPME tends to result in shorter fibre lifetimes, and where the matrix is extremely dirty, it might not be a viable option without prior pre-treatment of the sample to clean it up. One of the key reasons why SPME isn't adopted in mainstream testing is down to the poor lifetime of SPME fibres. Typically, these suffer from mechanical failure due to their very thin fibre tip. SPME performance can also suffer when samples have analytes at very different concentrations, where one concentration is high and the other is very low. SPME Arrow has been designed to overcome some of these issues by employing a larger probe that is significantly more rigid. It has a much higher sorbent surface area to boost sensitivity compared to standard SPME, and offers a wider dynamic range for analyte concentrations. The next technique is thermal desorption, or TD. This is a fairly common technique that has a very wide range of applications across most industries. Again, thermal desorption utilises a solid sorbent to trap VOCs and SVOCs in order to pre-concentrate samples by as much as 10 to the 6. This enables the analysis of concentrations well below that of conventional techniques. Samples are sampled onto a sorbent tube, which is a small stainless steel or glass tube packed with a sorbent material. Think of it as being like a very short packed column. In fact, some of the sorbent materials used in TD are also used as stationary phases in packed columns. When the tube is cold, analytes stick to the sorbent as they pass through it, trapping them in the tube. There are a huge number of ways of sampling onto this tube, making TD a very versatile technique, suitable for solids, liquids, and gases. The sampling technique usually depends on the application required. Passive sampling is where a tube is left in an environment and the analytes trap onto it through passive diffusion. This is commonly used for the monitoring of air near landfill sites. Active sampling is similar in that it is typically used for air analysis. However, active sampling involves drawing air through the tube using a pump. This enables more sample to be analysed, giving higher detection limits. It also helps in quantitation, as the volume of air sampled is known. Permeation testing can also be used to analyse the permeability of food packaging. Samples can also be taken from breath. Devices are commercially available that enable you to breathe into a mask containing TD tubes. These tubes can then be analysed for specific biomarkers that may be linked with cancer. Finally, samples can be placed directly inside an empty tube. In this situation, there's no sorbent at all. This is often used in order to comply with specific emission testing methods, such as VDA 278, which is used to test car components like plastic trims. Do remember though that these tubes will be heated for analysis, so putting in samples that melt, like candle wax and chocolate, is not really recommended. Tube-based thermal desorption requires a dedicated device for optimal performance. The tube is heated, releasing the trapped analytes into the carrier gas stream. This can be quite a slow process as the tubes are relatively large, and there's a lot of sorbent for the analytes to be released from. As we know from our session on the split splitless inlet, a narrow sample band is essential. So what we do is transfer the sample onto a much smaller trap, with a very small amount of sorbent material. This trap is cooled to ensure no compounds break through the sorbent. Once the sample has been fully desorbed from the sample tube to the trap is rapidly heated, releasing the analytes very quickly onto the column, to give much sharper sample peaks. At this point, the sample can be diluted to reduce column loading and to speed up transfer from the trap to the column for sharper peaks. Some TD systems offer the ability to recover the sample that's been split away, back onto a cool, clean sample tube, in case the sample needs to be reanalyzed. The next technique is pyrolysis, a technique which, whilst still quite niche, is growing rapidly in popularity, as more and more companies and research institutes look to novel ways of recycling plastics. Pyrolysis is literally the splitting of things by heat. In analytical chemistry, it's the splitting of large molecules like polymers using heat. These larger molecules would not by themselves be suitable to analysis by GC, as they do not readily vaporize. If, however, we heat them at high temperatures, they break down into smaller fragments known as pyrolysates. These are then suitably volatile for GC analysis. There are a wide range of applications, covering materials from plastics and rubbers right the way through to paints and wood. Pyrolyzers are, like TD instruments, very versatile in their operation. The most common way of using them is flash pyrolysis, often called single shot, where the sample is dropped into a very hot furnace to form pyrolysis products or pyrolysates. This can be used to identify polymers based on their pyrogram. A pyrogram is the chromatogram a polymer creates, containing peaks for all the associated pyrolysate products. Advanced software packages can analyse the chromatogram and associated mass spectra for each peak to accurately identify the polymer material in the sample. One technique that can be very useful for advanced pyrolysis method development is evolved gas analysis, or EGA. A sample cup is dropped into a cool furnace, around 50 degrees, and then heated gradually. Importantly, there are no analytical columns installed between the pyrolyzer and the detector. A thin tube with no stationary phase is used to link the two, allowing the detector to report the approximate quantity of material that is evolved at different temperatures. The technique cannot speciate the sample, but it can be used in method development to determine which furnace temperatures to use for the pyrolysis measurements. In the example on screen, there are two main regions, one corresponding to the thermal desorption of volatile analytes from the bulk material, and a second region relating to the breakdown of the material into pyrolysates at high temperature. This information can then be used to develop a double-shot or multi-shot method, where we analyse the same sample multiple times at different temperatures. In double-shot analysis, the sample is heated stepwise, firstly at lower temperatures to thermally desorb the volatile species without thermal decomposition. This generates its own chromatogram containing the volatile species present in the sample. The sample is then dropped back into the furnace to undergo flash pyrolysis. This can be an effective way of removing some complexity from the chromatograms by splitting the results onto two or more separate chromatograms. Not all instruments are capable of performing double-shot pyrolysis, so be sure to select your pyrolyzer carefully if this is something you're interested in doing. Some pyrolyzer furnaces can even be fitted with a catalyst bed. This enables companies to test catalysts on a micro scale to develop novel catalysts for industry and research. The red pyrogram shows the analysis of a seed cake. If we now introduce a zeolite catalyst into the pyrolyzer to react with the pyrolysates from the seed cake, we see very different products. We instead produce products that have a wide range of uses. Finally, let's have a look at gas sampling valves. After headspace analysis, this is probably the most common alternative sampling method, and is the most common method for analysing gaseous samples. In the most basic form, a gas can be injected manually using a gas-tight syringe directly into a split-splitless inlet. This can be suitable for qualitative analysis, but reproducibility is very poor. For higher reproducibility, we use a gas sampling valve fitted with a fixed volume loop. This is the exact same hardware configuration that's used for loop-based headspace sampling. These valves come in a variety of forms, but often look like the schematic on screen, with 6 fittings. These valves tend to be housed in a heated enclosure next to or on top of the GC oven. Here's a list of some of the common applications. These include the analysis of reactor products, the analysis of gas content in the hydrocarbon processing industry, purity analysis of high purity gases such as your GC carrier gas, and also for breakthrough testing of gas masks for chemical warfare agents. Let's take a look at a video of how a basic 6-port sampling valve works. The sample flows through a sampling loop of a known volume, typically somewhere between 50 and 1000 microlitres. Whilst this is happening, carrier gas flows through a separate line on the valve, directly onto the column. This ensures the column always has a flow of carrier gas through it. Once the sample loop is filled, the valve rotates. This puts the sample loop directly in the carrier gas flow path. The carrier gas then sweeps the sample off the loop and onto the analytical column. Here's a static diagram of the fill and flush flow paths, so you can study these in your own time. Brace yourself everyone, because unfortunately gas sampling gets a lot more complicated than this. In one of the recent Q&A sessions, we were asked how you manage water in samples when using an alumina column, which is not compatible with water. The answer is to use a 10-port valve with backflush. The same is true when using a molecular sieve column with analytes such as CO2 and ethane. These larger molecules get stuck on these columns, which means they need to be heated to very high temperatures for a very long time to remove them. By using a backflush valve system, we can prevent these components getting onto the analytical column. So let's see how it works. The sample is loaded through a loop in exactly the same way. We then have 2 sources of carrier gas. One flows through column 1, which is our pre-column, and the second flows through column 2, which is our analytical column, such as a molecular sieve. The valve is then switched, and the sample is flushed off the sample loop and through the pre-column. The analytes with a short retention time on the pre-column then continue onto the analytical column. If we time it correctly, when we switch the valve back, the first portion of sample makes it onto the analytical column and goes to the detector. Whilst the remainder of the sample, that was retained for longer on the pre-column, gets flushed back in the opposite direction and is vented from the system. Here's the 10-port valve in a static diagram. In the fill position, the system is essentially the same as the 6-port configuration, except we have an additional line that runs through a pre-column and out to waste. When we flush the sample, it flows through the pre-column and onto the analytical column. It's important we select a pre-column that retained the unsuitable analytes very well, but has minimal retention of the analytes that are safe to put onto the analytical column. Once all these analytes are past the pre-column, we switch the valve back again. Carrier gas 2 now provides gas flow down the analytical column to enable the sample to continue to the detector. Carrier gas 1 is then in line with the pre-column, which results in the flow being reversed through the pre-column. The analytes still on it are pushed back off the pre-column and travel through the restrictor and out to vent. If you thought that was complicated, many systems are unfortunately far more complicated than a single valve system. Some can have 2 or even 4 valves to fully separate and analyse the full range of analytes that are required for the method. This is particularly true in the hydrocarbon processing industry, where analytes from hydrogen all the way up to double-digit carbon numbers need to be quantified in a single analysis. Here's an example of a pretty extreme system that has 4 valves, 8 columns and 3 detectors. It generates 3 separate chromatograms in a single run, separating ultravolatiles like helium from hydrogen, right up to hexane. So there we go, a rather long whistle-stop tour of some of the many sampling techniques that can be used with gas chromatography. To try and give a visual overview of which analysis technique can be used with which types of samples, here's a table outlining the sampling techniques that are generally appropriate for the use with gaseous, liquid and solid samples. Hopefully this has demonstrated just how versatile GC is as an analytical technique. We've covered Headspace, SPME, thermal desorption, pyrolysis and gas sampling valves, and the wide range of applications these techniques can be used for. Next time we'll be travelling to the other end of the gas chromatograph to look at the choice of detectors that are available for GC. This session will look at the considerations to think about when selecting a suitable detector, the range of detectors available, and information about how each of them operates. We'll also look at the applications they're used for and their pros and cons. If you'd like to receive the latest news from Shimadzu UK, including information on webinars, workshops and events, please join our newsletter by going to our website. If you're joining this webinar from the UK, please use the contact details on screen to get in touch. For those joining from outside the UK, you can find contact details for your local Shimadzu office by visiting Shimadzu's global analytical website. That's all from me for this week. Thank you very much for your attention and enjoy the rest of your day.
Excellence in science. Shimadzu.